Hi, this is Mrs. LaBarbara. Today's topic is describing motion with VT graph, part 1 slope. The objectives for today are know the meaning of slope for VT graph, understand the relationship between the slope and acceleration, be able to describe motion with a given shape for a VT graph, be able to determine the slope on a VT graph. The meaning of slope for a VT graph. So here is velocity versus time graph. The slope is change of y divided by change of x. Change of y in this case is change of velocity. Change of x in this case is time. By definition, this is the acceleration. So slope equals to acceleration. The slope of the line on a VT graph is equal to the acceleration of the object. Describe motion with a given shape for a VT graph. The slope of the line on the velocity time graph reveals the acceleration of the object. So the slope in the graph on the left is 0. So we know acceleration equals 0. We can also see velocity is constant positive. Actually, it's 10 meters per second. The second graph, we can see the slope is constant and positive, so acceleration is constant positive, and we can see as the time increases, velocity increases by the same amount. Example, equilibrium means acceleration is 0 and velocity is constant. So which graph best represents the motion of an object in equilibrium? So in other words, which graph tells you the velocity is constant? Let's take a look at the first graph. First graph is displacement versus time. In displacement versus time graph, slope is the velocity. And we can see the slope is constant. So the first graph tells us the object is in equilibrium. Take a look at the second graph. The slope is not constant. The slope is changing. As a matter of fact, slope is increasing over here, then over here, getting steeper. So this is not in equilibrium. That means velocity is increasing. The third one also tells you velocity is increasing. Not in equilibrium, not in equilibrium. The last one, you probably say, wait a second, isn't line straight? Isn't that constant also? Yes, what is constant? In velocity versus time, the slope is acceleration. Acceleration is constant, non-zero. The slope is not 0, so this is not equilibrium. The answer is A. Another equilibrium question. This is opposite. So which graph best represents a motion that is not in equilibrium? In other words, which one tells you velocity is increasing and acceleration not 0? Let's take a look at the first graph. This is distance versus time. What's the difference between distance versus time and displacement versus time? In distance versus time, the slope is speed. In displacement versus time, the slope is velocity. So this one tells you the speed is constant. Well, let's see, the object also travels a straight line. So if the speed is constant and it's moving a straight line, that really means its velocity is constant. So this is in equilibrium. Choice B, this one says the object is at rest. If the object is at rest, it's also in equilibrium. This one tells you the speed is constant. Since it's traveling along a straight line, this means velocity is constant. It is in equilibrium. The last one, this one says the speed increases as the time increases. So if the speed is increasing, velocity is changing. So this is the one not in equilibrium. As a matter of fact, we know from this one, since the slope is constant, acceleration is constant. So the answer is D. Direction of velocity on the VT graph. So here is VT graph for different ones. How do we know which way the object is traveling? The velocity would be positive whenever the line lies in the positive region. So this is in the positive region, this is in the positive region. So we know these two, the velocities are positive. Similarly, the velocity would be negative whenever the line lies in the negative region below the x-axis on the graph. Take a look at this one. This is below. This is negative velocity. And finally, if the line crosses over the x-axis, if this line crosses over, that means the object is changing direction. So you have a big velocity, becomes smaller and smaller, becomes zero. Then you're traveling in the opposite direction. Think about a ball goes up, you throw a ball, go up. At the highest point, it stops, then it comes down. That is changing direction. That will cross this horizontal line. Speeding up or slow down on the VT graph. Speeding up means the magnitude of the velocity is getting larger. Not the negative doesn't matter. See, this is getting more and more negative. The magnitude, the number is getting larger. This number is also getting larger. So this is speeding up. On the other hand, the number is getting smaller. The number is getting smaller. This is slowing down. Let's just review about acceleration. What can we say about acceleration on this graph? Acceleration is a slope, positive, constant. So acceleration is positive. This one, acceleration is a slope, it's constant and negative. Acceleration is negative. This one, slope is negative, acceleration is negative. Slope is positive, acceleration is positive. Remember, we learned before how to determine the direction of acceleration. We said if the object is speeding up, acceleration and velocity have the same sign, positive, positive, negative, negative. If it's slowing down, acceleration and velocity have opposite sign. Velocity is positive above zero, acceleration is negative. Velocity is negative below zero, right? Acceleration is positive, opposite. So just a little review. Let's take a look at this example. Consider the graph shown. The object whose motion is represented by this graph is include all that are true. So this one shows velocity is positive because it's above zero, velocity is decreasing. That means you're slowing down. And you also know acceleration is constant negative. So let's see. Is it moving in the positive direction? Yes. How do we know? Because velocity is positive. Is it moving with constant velocity? No. Velocity is getting smaller and smaller, approaching to zero. Is it moving with a negative velocity? No. Velocity is above zero, it's positive. Is it slowing down? Yes. So first it's moving in the positive direction. Is it slowing down? Yes. Is it changing direction? No, because it did not cross the horizontal axis. Is it speeding up? No, it's getting smaller and smaller. Is it moving with positive acceleration? Is the slope positive? No. Is it moving with a constant acceleration? Is the slope constant? Yes. So it's A, D, and H. Now let's describe velocity and acceleration in all these graphs. What can we say about velocity? Constant. Velocity doesn't change. Positive, constant. What can we say about acceleration? Zero, because the slope is zero. Velocity is positive, constant. Acceleration is zero. What can we say about this velocity? This is negative, below zero, and it's also constant. What can we say about acceleration? Zero. Next one. So this one is saying, okay, as you can see, this is kind of like the ticker tape data, right? The space getting bigger and bigger. So there is acceleration. What can we say about this V? V is positive, increasing. What can we say about A? A is a slope. A is positive, constant. What can we say about V? First, it's positive above zero, and it's decreasing, corresponding to this diagram also, right? What can we say about A? A is a slope, constant and negative, or negative, constant. What can we say about this V? Below zero is negative. It's getting smaller and smaller, approaching to zero. What can we say about A? A is the slope. Slope is positive, constant. What can we say about this V? V is increasing in the negative direction because it's below 0, negative increasing. What can we say about this A? A is the slope. Slope is negative constant. Next one, determine the slope on a VT graph. So this is very similar as determine the slope on a DT graph. So we have the same steps. The most important thing is to pick the two points on the line. If the points are not on the line, you will get the whole thing wrong. Next one, determine the difference in the y coordinates. Then you determine the difference in the x coordinates. Then you divide the two. Remember, it's y over x. Then you have to show your units in your work. Example, the velocity versus time graph for a two-stage rocket is shown below. Determine acceleration during the listed time interval. T equals to 0 to 1 second, 0 to 1 second. Acceleration is the slope. So we use change of y, which is 40, divided by change of x, which is 1. You will have 40 meters per second squared. Now, acceleration between 1 to 4 seconds. 1 to 4 seconds, that is the slope. So similarly, you pick the 2 points, 100 over here, minus 40, that's the y, divided by x, 4 minus 1, that's the two corresponding x points. So you should have 20 meters per second squared. That makes sense because the slope is the acceleration. As you can see over here, between 0 to 1 second, slope is steeper than from 1 to 4 seconds. Now, how about 4 to 12 seconds? You use the same idea. 12, the y is negative 60 meters per second. The other y is 100. So negative 60 minus 100 divided by 12 minus 4, you should have a negative 20. The slope is negative. It's 20 meters per second. As you can see, this is an example of changing direction. So basically, this describes the motion of the rocket. You'll have higher acceleration than constant lower acceleration. You will have maximum speed. Then you're still traveling upward. You're slowing down. Eventually, you become 0. Your velocity becomes 0. Then you start to travel downward, but with the same acceleration as before. That's it for today. See you next time.